Okay, so as I mentioned earlier, for self-adaptive or more configurable system on chips, which are not performance very much performance dependent, it would most likely be preferable to use a CPU and some sort of hardware architecture. However, if you are dependent on performance, or power consumption, or size, then FPGAs are typically used instead of a common CPU. So just to give you a little bit of a brief overview of what an FPGA is. The FPGA is built by what's called slices and data pathways and clock pathways and specific memory and so forth and so forth. However, the sort of main component is this sort of port with a lookup table, which typically there's a specific number of LUT ports in each slice, dependent on the supplier of the FPGA and so forth. However, that's not really that important. What is important though is how it works. So, as you can see here, here's a gate or a port. We have 3 inputs, A, B, and C, and 1 output, and also a carry output, and a clock input, and there should also be a carry input maybe. Anyway, 3 inputs, 1 bit each, and 1 output. So the output is determined by the input, A, B, and C, based on a table. So in this specific example, I have chosen that if A, B, and C are 0, then the output will be 1. And if A is 0, B is 0, C is 1, then the output is 0. And if A is 1, B is 1, and C is 1, then the output is 1. The point being that these values are stored in a memory location. And based on the values in that memory location, well, that's how this specific gate will act. And as mentioned, in an FPGAs, there are millions of such gates who acts according to the memory values in specific locations. That's how FPGAs work. So, as I mentioned in the car example, what they did there was that the values in memory were altered in order to change the performance of the system. Now, a similar thing can be done for FPGAs, and I will show an example. So this is a very, very basic example, very simple, I would say. Let's consider a bitwise addition. Okay, so and with 2 inputs, A and B, 1 output and 1 carry output. If you add 0 and 0, you will get 0 and carry 0. If you add 0 with 1, you will get 1 and the carry will be 0. If you add 1 with 0, you will get 1 and carry 0. If you add 1 with 1, you will get 0 and 1 as carry. Bitwise addition. So let's look at bitwise multiplication, which, well, it's a bit silly, but I will use it in this example anyway. If you have 0 times 0, you will get 0 out and 0 to carry. 0 times 1, 0. 1 times 0, 0. 1 times 1, 1, and 0 to carry out. So if we try to imagine that those specific values could be placed in lookup tables, then you could have one lookup table performing addition and one performing multiplication. However, if you want a self-configurable device, an example of such a device or such could be a very simple device that can either do hundreds of bitwise additions or let's say millions of bitwise additions, or millions of bitwise multiplications. Maybe I should have used subtraction instead of multiplication, but the point still stands. So here I have drawn 3 gates, each with 2 inputs, 1 output, and 1 carry output. So let's, if you want all of these to do addition, you could use this lookup table, or this information could be in the lookup table. If you want all of them to do multiplication, this could be placed in the lookup table. So, this is pretty simple. I mean, you could easily have dual lookup tables for these gates, and then you could have maybe a third input which selects whether you will be using multiplication or addition this time around. And this, it would probably be common for all of them. So then the user of this device can select, okay, I want you to add all of these bits, separately, or I want you to multiply them. And it could be selected based on this. This would mean that you have one physical device with 2 million, or 1 million A inputs, 1 million B outputs, and 1 million outputs, and 1 million carry outputs. And based on this one bit here, you could select them to either act as this or as this. This could, it could also be done, they could also have a common LUT, actually. If they all got access to the same LUT, then they would have a common LUT, and you wouldn't have to waste the space, each of them, if this is the only purpose of this specific device. Anyway, the point is that this is a very low operation that can be, you can change between 2 operations for one device that is in the field, and we can easily change back and forth by just changing this bit between 1 and 0. So if this, for example, was in a graphics card for a computer, then instead of addition and multiplication, it could be multiplication and division, and you could either zoom in for something, or you could zoom out from something, right? And then you will get vectors as input, and based on some value, you would either zoom in or zoom out, and that these vectors will be shown on the screen. And this is only relevant for applications that are dependent on performance, such as a graphics card. Like a graphics card has to, for a common screen, you update the pictures typically 24 times each seconds, I think, or 60 times, so dependent on the screen. So these calculations have to happen very fast. And that is when this type of logic comes into the picture. Now, back to, let's continue on this train of thought and look at what would happen if you had some sort of computer or CPU that would control the contents of the lookup tables. Well, then the possibilities are limitless. I mean, it's crazy almost. However, it's also crazily complicated. As one of the first things you realize when you start programming FPGAs is that the software tools that transforms the Verilog or VHDL source code into information that goes into the FPGA's lookup table, this software is extremely complex. And this, just based on the time it takes from you press the button until the program is ready, you really realize how complex it is. So to make such systems, it will take a lot more than what I have explained in this simple example. It will be a very challenging task. However, it is impossible. No, I mean, it is not impossible, but it is difficult. And also, as I explained in the car example, for a system, this example right here, the system doesn't really adapt. It just reconfigures itself based on the input from the user. But in the car example, the system adapted based on what it learned, basically. And it's pretty understandable in such a simple example. But if you want to apply something like that, if you want a computer system to learn the same way as we humans learn, then it's a challenging task. And it's very interesting and challenging. And the part of the challenge is that what kind of in order to learn, you have to be able to compare what you have learned with something else. In the example of the car, the transmission could compare today's acceleration with yesterday's acceleration. And so that's pretty easy. Okay, you learn that, okay, this guy he accelerates faster than the other guy, then I will adapt. So the question is, how do you create such a database for a computer to learn? Yeah. Okay, I think I'm going to stop there. And yeah, thanks.